Today, we're diving into the world of color to unravel the secret behind a really special kind of dye.
You know, we all think we get how dyeing works. You take some colored liquid, you put the fabric in, and the fabric soaks up the color. Simple enough, right?
But what if the color wasn't even there to begin with? What if you could take two totally colorless liquids and a bright, vibrant dye was literally born inside the fibers of a shirt?
Yeah, this isn't science fiction. This is the amazing world of azoic dyes, a unique process where the color is actually synthesized, not just slapped on. So here's the key thing to wrap your head around. Unlike most dyes you buy pre-mixed, azoic dyes are made from scratch during the dyeing process. It's kind of like having a tiny chemical factory running right there on the cloth. And because this whole method is so unique, these dyes have picked up some really cool nicknames over the years. Ice color, magic color. By the end of this, you're going to know exactly where those names came from. Okay, so the whole process kicks off with two key ingredients. Think of them like two puzzle pieces that on their own don't look like much, but when they snap together, that's when you get the color.
These two components are called naphthalene and a diazo base. And here's the wild part. Both of them are completely colorless by themselves. If you looked at them in two separate jars, you'd just see clear liquid. Nothing special.
So, how in the world do two colorless things make a color? Well, the secret is in the chemical bond they form. When the naphthol and the diazo base react, they create this special structure called an azo group. You can think of it like a chemical bridge. And once that bridge is built, it's able to absorb and reflect light in just the right way that our eyes see it as color.
And here it is. This is what that little bridge looks like on a molecular level. That simple N double bond and structure, that's the heart of it. That's the engine that literally creates the color out of nothing.
Okay, so we've got our two colorless components and we know they need to connect. But how do we get them to meet up inside the fabric? Well, it happens in this really precise three-step chemical dance.
This dance has three main moves. First up is naphthalation, which is just prepping the fabric with the first ingredient. Second is diazotization, getting that other component ready. And then finally, coupling. That's the grand finale, where the two meet and the color just appears.
So in step one, the fabric gets a good long soak in a solution of naphthol. The fibers just drink this stuff up, this first colorless ingredient, loading them up and getting them ready for the main event. Meanwhile, in a totally separate container, we're getting the second component ready through a process called diazotization. And pay close attention here. You can see it says ice temp. That little detail is absolutely critical, and it's our first big clue to solving the mystery of those nicknames. And now for the final act. We take the fabric, which is already loaded up with that first colorless chemical, and we dip it into the second bath. The two components instantly find each other inside the fibers. They couple together to form that azo bridge, and bam! A deep, rich, insoluble color just appears out of nowhere.
So, now that we've walked through the process, let's connect the dots. It's time to solve the case of those mysterious nicknames.
Let's tackle the first one. Why on earth would anyone call a dye ice color?
The answer is right here in this number, 0 to 5 degrees Celsius, basically the temperature of ice water. Remember that second step, diazotization? Well, it turns out that reaction is super unstable at room temperature. For it to work at all, it has to be done in a bath that is kept literally at ice temp. So the name isn't a metaphor, it's a critical instruction for the person doing the dyeing.
And that brings us to magic color. I mean, just picture it. You take a piece of plain, colorless, wet fabric. You dip it into another bath of what looks like just plain water, and instantly a deep, rich color explodes into being. It just appears from nothing. For all the world, it looks like a magic trick.
So this is a seriously clever process, right? But all that magic and chemistry, it does come with a few trade-offs. Let's break down the pros and cons.
Okay, on the plus side, because that dye molecule is built inside the fiber and it's insoluble, it has fantastic washing fastness. It doesn't fade easily, and you get these incredibly bright, vivid shades. But on the flip side, it has poor rubbing fastness, we'll get to that, a pretty limited range of colors, and trying to match shades exactly is a real headache because you're controlling a live chemical reaction, not just following a simple recipe.
So that poor rubbing fastness, that's the biggest issue. See, while most of the color forms deep inside the fibers where it's locked in, some of the reaction just happens on the surface.
And that surface-level pigment isn't trapped, so it can literally rub off on your hands or on other clothes.
But let's circle back to the main reason you'd go through all this trouble. The final color is insoluble in water. That means once it's locked into that fiber, it is staying put, which gives it that incredible performance in the wash.
So what this all really boils down to is that this isn't just dyeing. This is straight up chemistry in action, happening right on the fabric itself. It's a powerful reminder of all the invisible science that's woven into the things we use every day. And it just makes you wonder, what else are we missing?